This is a second recording for section 11. This is the second recording for section 11.4, probability in genetics. Gregor Mendel, an Austrian monk, used the idea of randomness to establish the study of, that should be genetics, not generics. To study the flower color of certain pea plants, he found that a pure red plant crossed with a pure white plant produces red. Thus, he theorized that red is dominant, and we symbolize, or we use capital letters to stand for the dominant gene, and then white is recessive, and that's little r. The pure red plant carried only genes for red, and the pure white carried only genes for white, right? When we talk about pure red, that is two dominant genes. And I've already mentioned this, right? The dominant gene is the capital letter, right? Suppose that a second generation pure white flower is crossed with a second generation red flower, right? This is red because red is dominant, right? And so a dominant with a recessive, of course, will become, right, this dominates over the white, so it will become red. So they're crossed. If you did some of these in biology in high school, you use these Punnett squares, right? Up here was the white flower with little r on the side. Doesn't matter which place you put them, right? But one crossed with the other, and you made a little square. Right, one across the top and one down the side, and then you just put them in the square. This one would be one dominant, one recessive. Again, one dominant, one recessive. And this box, right, this would be two recessive genes, and here as well, two recessive genes. Okay, so this is what the square would look like. And remember that anything besides little r is red, right? Because red is dominate. So if there's one dominant gene, right, then it will be red. So what is the probability that the offspring is red? Well, that's actually 2 of them out of the 4 possibilities. So it's half. And the probability it's white are those 2, right? That is the only way to get white, is to have 2 recessive white genes. So that is also half. We'll do one more example of these. Cystic fibrosis is one of the most common inherited diseases in North America. If we denote the cystic fibrosis gene with a little c and a disease-free gene with a capital C, since the disease is recessive, right, it's not use big C if they have it, right? Actually, cystic fibrosis, actually getting the disease is recessive. Then only a little c person will have the disease, right? Because little c indicates that they actually have the disease, since that's recessive. A child can also inherit a disease from 2 carriers, right? Big C, little c, right, means that they are a carrier, but they don't have the disease, right? Suppose 2 cystic fibrosis carriers have a child, right? So we know this person, or someone with, why is that right? No, it didn't. Just to remind you, that is recessive. It has the disease. One recessive and one dominant means carrier, but they don't have the disease, since having the disease is recessive. And only someone with 2 Disease-free genes. I will be disease. Find the we suppose 2 cystic fibrosis carriers have a child, so our carrier is 1 dominant, 1 recessive. It doesn't matter the order that you put them in again. And fill in your chart. So this is little c, this is little c, big C, big C, little c, big C, big C. All right, just fill in the square. And then it says, find the probability that the child will have cystic fibrosis, right? And having cystic fibrosis would be having these 2 recessive. So that is 1 out of the 4 possibilities. Find the probability that the child will be a carrier. Right, carrier is 1 recessive, 1 dominant, so that's actually 2 out of the 4, which is half. And of course, there's a 1/4 chance that the child will actually have the disease or not have the disease. Right. So now we're going to look at some experimental probability. A cup is flipped 100 times. It lands on its side 84 times, on its bottom 6 times, and on its top 10 times. Find the probability that will land on its top. So we've done this experiment 100 times. Maybe we should really do it 1,000 times to get a better estimation of the true probability of this, of where it might land. Find the probability that will land on its top. It landed on its top 10 times out of the 100 times that it was flipped. And of course, you would just cross out a 0 or divide top and bottom by 10, and you would get 1/10. Find the probability that will not land on its side. Well, it landed on its side 84 times, and it landed on its bottom or top 6 and 10, so that's 16 times it did not land on its side out of 100. So you could also do 100 minus 84 to get 16, or you could just add up the other 2 possibilities. And if you want to, if it asked you for a reduced fraction, you could divide top and bottom by 4 to get 4 out of 25. If it asked for a decimal, you could 1600ths, would be 0.16. So either way is fine. So this is an example of experimental, which we also call empirical probability. So the law of large numbers tells us as an experiment is repeated more and more times, the proportion of outcomes favorable to any particular event will tend to come closer and closer to the actual theoretical probability of the event. Like we know that the theoretical probability of flipping a head with a single coin is of course 50% chance. All right, so it's 0.5 or 1/2. But if we took and flipped a coin 10 times, we might actually get 6 heads and 4 tails. Right, so that would actually be 6 out of 10, 60%. Right, but the more times we flip, if we flip it 1,000, right, we expect it to be close to 500. It might be 505, right? But the more times we flip, the closer and closer it will approach the theoretical, right? This is experimental when we do it 10 times, but it will approach the theoretical probability of 50%. The last example in this section, it gives you a chart, and it looks like there are males and females, married, never married, divorced, widowed. If a person is selected at random, find the probability, round to the nearest hundredth, that the person will be male. So if you look at it, here is actually the table total. This is the number of males, the number of females. All right, those, if you add those up, those should total 242. But also, if you total up these four things, they should also total 242 as well. The number of married, never married, divorced, and widowed. Those should total 242. So the total number of people is 242. So if we want the probability of male, all right, we take all the total males. It doesn't matter if they're married, divorced, whatever. The total number of males is 118. And it says to round to the nearest hundredth, so I'm not even going to bother trying to reduce that fraction. I'm just going to hit 118 and the divided by button on the calculator, 242. If you do that, you get 0.487, so to the nearest hundredth, I know it's going to be 0.49 because the 7 is larger than 5. What is the probability that the randomly selected person is never married? We add up the males and females for never married, and they total 74. So that's 74 out of the total 242. If you hit 74 divided by 242, you get 0.305, which rounds to 0.31, since this digit over here is greater than or equal to 5. And the last one, find the probability that the person is a married female. So married females, that is 65, right? Married and female. So that's 65 out of the 242. So that's 0.268, which will round to 0.27. So that is the end of section 11.4.